Alrighty, 8.9 HH equation. So obviously we've talked about the HH equation before. We talked about it in 8.4, we talked about it in 8.5, and so some of this is review, some of this is a little bit new, but the calculations are pretty similar to what we've already talked about before. So, quickie review. On our constant equation sheet, this is based off a weak acid and its conjugate base. And so we have Ka because it's a weak acid, we have our conjugate base on the top, and then we have our weak acid on the bottom. So just reiterating that. Again, this is the generic form. You would just put whatever weak acid here and whatever conjugate base up here. Okay. Now, we have two buffer systems though. We have weak acid and conjugate base, or we have the weak base and conjugate acid. And so this equation is for weak acid and conjugate base. We could change it so we're talking about instead a weak base and a conjugate acid. Now remember, this HH equation is only for buffers. So you only calculate this when you have a buffer. When you have the weak acid and the conjugate base usually in a salt, or again the weak base and conjugate acid usually in a salt. And if you're unsure from section 8.5, if you're halfway to the equivalence point, the HH equation will not fail you. So as long as you know you're in the buffer system, just use the HH equation and you should be able to calculate pH. Now, as I've said earlier, there's two buffer systems. So we could write down the buffer system for a weak base and its conjugate acid. And so instead of pH, we can calculate pOH. And since it's a base, we can talk about pKb instead, so the equilibrium constant of a base. And then we'll log. And so on the top, we're going to have our conjugate acid, so the Hb+. And then on the bottom, we'll have our base. So again, the top is going to be our conjugate acid, and our bottom is going to be a base. So remember that. You can easily interpret this just from this, so it's not like memorizing hella, it's just being able to interpret it for a different system. Now sometimes if you have a different system, you could still use this equation. It really depends on how the problem is worded. So it depends on the examples. So, as a reminder, calculations for buffers is to resist pH whenever you're adding something to the system. So H plus or OH minus, for example, is added to the system. And so here's an example. So if I have acetic acid and I have its conjugate base here, I have a pH of 4.74, okay? Now, if I add some sodium hydroxide to that, notice the pH changed from 4.74 to 4.76. And so it's a base, so it increased in pH because, again, going higher on pH is increasing how basic it is. And notice it barely changed. It went from 4.74 to 4.76. So you only have 0.02 of a difference between here and here. So you want to be very mindful of that. The buffer is trying to keep pH steady. That is what a buffer is trying to do. So here is an example calculation. So go ahead and read this problem real quick. Alrighty. And so when we read this problem, one thing you should automatically recognize is that it's a buffer. And the reason I can tell it's a buffer is because we have a acid, the lactic acid, and then we have its conjugate right here. So the conjugate part is right here, and then obviously this is the acid. So you want to be careful about that because students don't notice that sometimes, and then you would not be able to calculate this at all. So you should be able to see, hey, look, it's a buffer because I have an acid, and then I have its conjugate base, because remember this ionizes completely in solution based off the solubility rule you had to memorize. So because it is completely ionizing, we are with the conjugate base and its weak acid. And so pretty much I would just take the HH equation because it's a buffer system. And so here's my HH equation, and I'm literally just going to plug in everything from our problem. Now I forgot molarity here, so don't forget molarity here. And so we put our Ka here, and then we're going to put our conjugate base on the top, and then we're going to put our weak acid on the bottom. And so I'm literally just plugging it in. Remember that p to anything is negative log of that anything, and so that's why I put negative log of the Ka value. And so I just plug that into my calculator, and I get 3.38. Cool. So you should be able to plug stuff in. Again, p of anything is negative log of that anything. Coolio. All right, here is example 2. So, similar problem. We have NH3 and we have NH4Cl. So we have ammonia and ammonium chloride. We have a Kb value. Cool. Now, let's say we want to calculate pH. So there are multiple ways of doing it. I'm just going to show one way of doing it. So if I want to just use the HH equation as is, notice it's pKa, but I have Kb. And so if we go back to our constant equation sheet here, I have a conversion between Ka and Kb, assuming we're at room temp. So room temp is 25. As a reminder, a problem that doesn't give you temperature, we assume it's room temp unless otherwise stated. So I can take this Kw equals Ka times Kb, and I can use this constant here in order to solve for Ka. So Kw is that. I reorganize it because I'm trying to solve for Ka. I plug in Kw constant from over here, and then the Kb value from over here. And so I calculate that on my calculator, and I get that value. So then I go back to the HH equation. I'm going to plug in pKa, so negative log of this number, and then the original values that were given earlier. And so pH is that, and then we got the log of the other guy, and then we plug that into our calculator, and we got 9.02. Now, as a good practice to do, you should always check if this answer makes sense. So if I go back to the problem, I have NH3 with a Kb value that's less than 10 to negative 7, and so that means this is going to be a basic buffer. And so basic pHs are over 7, and since this is over 7, that answer does make sense. So that's a good way to check. Cool. All right, here is an MCQ, and here's a chart. So look at the Ka values. We have the different acids here that are listed, and then we have different pairs. So go ahead, read this MCQ, see if you can figure it out, and then I will talk about it in a few moments. Alrighty, ready? Here we go. So, when combined in equimolar amounts. So what does equimolar mean again? Well, if we break it apart, equi is equal, and molar is moles. So we have an equal amount of moles. So the amount of moles of acid equals the amount of mole of base. So if I go back to that HH equation from earlier, right here, the part here of the HH equation, the log part, that is going to be equal to 1, because whatever the volume is of these buffers systems can be, they're going to have the same volume. So, and since the moles of each of these are the same, the molarity of the conjugate and the weak acid are going to be the same. And so that means this is going to be log of 1. Log of 1 literally equals 0. So that means my pH is going to be equal to pKa. And so I can look at these Ka values, and I could use a calculator if I wanted to and plug in all those Ka values into negative log of Ka to see which one is closest to pH of 7.5. I could also logic it out without using a calculator just to save me time. So one trick about logging stuff is you can look at the exponent here. So since we're negative logging, the negatives are going to go away in your answer when doing negative log of these guys. And if you have a value here that's more than 1, then your exponent is going to be 1 less than what you would calculate on a calculator. So for example, this number here, 4.0 times 10 to negative 4, if I negative log that, the answer is going to be like 3 point something. So I don't need to know exactly what it is. I just know it's 3 point something. And so the next one, because this is more than 1, if I negative log this whole answer, my answer is going to be based off the exponent, but a little less. So it's going to be 4 point something. And then the third option here is negative 8. And since it's more than 1 over here, it's going to be 7 point something. And then for this one, it's negative 10, this is greater than 1, and so it's going to be 9 point something. Since we're trying to get close to 7.5, I could just pick this one, the HClO and the ClO minus. Now, when you're looking at these, again, remember, check, is it a weak acid? And then check, is it with its conjugate? Because the answers might not be. So you want to be very careful about that. Cool. All right. So here is an example FRQ with various parts. As it says here, some are previous sections of this unit, some of this is new. And don't forget this. There's also a K value that's written in the problem that I did not include in the example paper, so make sure you have that. And see if you can solve this before looking at the answer. So pause the video, try it out. All right, ready? Here we go. So I wrote KB because NaOCl, well, OCl minus is going to be the ion that's in solution. And so since OCl is in solution, that would be a base because it can grab an H because it's negative. And H plus is positive, so it can grab an H. And so therefore, OCl minus can be a base. Okay, so make sure you can recognize that. You can also look at the hydrolysis reaction. So you see here, and then you have the H being donated right here, so you notice it's a base. So that's the other way of logicking it out. And then remember, it's products over reactants. You see that the coefficients of all of these are 1s. There's no superscript on any of these. And you don't include water, because water is not part of the equilibrium constant. Then I could calculate the value of the equilibrium constant at 298. The K value was given earlier. I could do KW because this is room temperature, 298, so I get KB. And so from there, I could, yeah, that's pretty much all it was for that. And so then for the next part, you do a rice table, just like we've done many times. You don't fill out the water because it's a liquid. And then you plug in your E parts on the equilibrium constant. And then you do the math. So you solve for X. When you solve for X, you're technically solving for hydroxide because X is right here. So that's why X equals the concentration of hydroxide. And so I get that. And so, yeah, cool. Now, if we're preparing a buffer solution with some stuff, we can now calculate the concentration of the H3O plus. So if I have a pH, I could do the opposite of logging. So I move the negative to the other side, and then I could base 10 it. And then since it's base 10, because that's the opposite of login, then I can get the H plus in there, and so I can get my concentration. And then I use the HH equation in order to solve. This is not from the previous slides, right there. Well, whatever. So there we go. That's literally it for this section. So make sure you can calculate using the HH equation. Make sure you can combine stuff from the previous sections. But honestly, that's it. Okay, bye!